Welcome to the Power Electronics class. Myself B. Veerinarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are in second unit, AC to DC converters. In the last class, we are discussing the three-phase full-wave control converter with R load. We see that different output voltage waveforms for different firing angles. So in this class, we just derive the average DC output voltage for this R load. Later we go with the RL load. So here, this is the circuit diagram representation of three-phase full-wave control converter with R load. It consisting 6 SCRs which are numbered as T1 to T6. Out of these, T1, T3, T5 are called the positive group SCRs. T4, T6, T2 are called the negative group SCRs. And the phase difference between two consecutive positive group SCRs is 120 degrees, and the phase difference between two consecutive negative group SCRs is also 120 degrees, and the phase difference between positive group SCR to the negative group SCR is 60 degrees, and each SCR conducts for 120 degrees. And you keep those points in your mind, and these are the different output voltage waveforms. For alpha is equal to 30 degrees, for alpha equal to 60, and for alpha equal to 90. And these are the timing diagrams for different firing angles. Depends upon this timing diagram, we will tabulate the output voltage table. Depends on this, we draw the output voltage waveform. So from these waveforms, you conclude that if alpha less than 60 degrees, then the three-phase full wave control converter with R load is operates in continuous conduction mode, and alpha greater than or equal to 60 degrees, it should be operates in discontinuous conduction mode. Observe here, if you choose alpha 30 so you have some output voltage. If you go through the resistive load, current is in phase with the voltage, the current never reaches the reference line, so it should be operates in continuous conduction mode. If you observe here, alpha is equal to 60, at this instant the output current is 0. If you choose alpha equal to 90, from 0 to 30, 60 to 90, 120 to 150, in that interval the current is 0. Hence why the converter is operates in discontinuous conduction mode. So first we go with the average DC output voltage in continuous conduction mode. So here, first case, average DC output voltage in continuous conduction mode, that is alpha less than 60 degrees. So average DC output voltage V0 is equals to how many pulses you have generated for completion of one full cycle. How many pulses generated in the output voltage waveform? See, this is 1, 2, 3, 4, 5, up to 360. Here VCA is half, and here VCA is half. Total 6 pulses you are generated. If you choose alpha equal to 60, how many pulses you have generated? 1, 2, 3, 4, 5, 6, up to 360. For completion of one full cycle in the source voltage, we are able to generate 6 pulses in the output voltage waveform. Hence why that is simply called the 6-pulse converter. The three-phase fully controlled converter with R load is also called 6-pulse converter. Why? Because in the output voltage waveform, we are able to generate the 6 pulses for completion of one full cycle in the source voltage. And limitations are, if you choose alpha is equal to 30, take VAB as the reference. If you choose alpha is equal to 30, what is the duration of the VAB? 90 to 150. 90 to 150. Each line voltage will be present 60 degrees. If you choose alpha is equal to 60, what is the VAB? 120 to 180. 120 to 180, right. If we choose alpha is equal to 0, Where the VAB you are getting? VAB, this one, 60 to 120. If you choose alpha is equal to 0, the duration of the line voltage VAB is from 60 to 120. If you choose alpha is equal to 30, 90 to 150. If you choose alpha is equal to 60, 120 to 180, then how can you write the limitations? Simply for this 0, 60 to 120, you add firing angle, that is 60 plus alpha to 120 plus alpha. Then you have the output voltage like simply here V0 is equals to, we are getting 6 pulses for completion of one full cycle in the source voltage, and the limitations are 60 plus alpha to 120 plus alpha. How much voltage you transmit? Line voltage. So Vm sin omega L, VML sin omega t, d omega t. So by simplifying this expression, what you will get? So finally 3 VML by pi, integral sin omega t is minus cos omega t between the limits 60 plus alpha to 120 plus alpha. Replace the limits, 3 VML by pi minus cos 120 plus alpha, minus of minus plus 60 plus alpha. What you will get here? 3 VML by pi and this minus cos 120 plus alpha is written as 180 minus 60 minus alpha plus cos 60 plus alpha. We will write like this, na? Why? Because cos 180 minus 60, 120 minus of minus plus alpha. So we will write this cos 120 plus alpha is written as 180 minus 60 minus alpha. Cos 180 minus theta, minus cos theta, minus of minus plus. What you are getting here? V0 is equals to 3 VML by pi cos 60 minus alpha plus cos 60 plus alpha. So what you are getting here? Cos of A minus B plus cos A plus B. What is the formula? 2 cos A cos B. So that is 3 VML by pi 2 cos 60 cos alpha. So what is cos 60? 1 by 2. So V0 is equals to 3 VML by pi cos alpha. Cos 60 is 1 by 2, na? So 2 gets cancelled, and finally we are getting V0 is equals to 3 VML by pi cos alpha. That is the average DC output voltage of this fully controlled converter in continuous conduction mode. In continuous conduction mode. Similarly, case 2. Here average DC output voltage in discontinuous conduction mode, that is alpha greater than 60 degrees. Here V0 is equals to, see output voltage waveform. Here if you choose alpha equal to 60, VAB will appear from 120 to 180. Okay. If you choose alpha equal to 90, what is the duration of VAB? 150 to 180. If you choose alpha is equals to 75, then 135 to 180. Then how you will write? If you choose alpha is equals to 90, 150 to 180. If you choose alpha is equal to 60, 120 to 180. Then how you will write that? Limitation here 60 plus alpha, right? So under discontinuous conduction mode, the average DC output voltage is given by, here also you are getting the 6 pulses. So 6 by 2 pi integral 60 plus alpha to 180 and VML sin omega t d omega t. And so by simplifying this expression, 3 VML by pi integral cos sin omega t is minus cos omega t between the limits 60 plus alpha to 180. So what you are getting here, 3 VML by pi minus cos 180 is 1 plus cos 60 plus alpha. Here this is the average DC output voltage of 3-phase fully controlled converter with R load in discontinuous conduction mode. Right. Next one. Three-phase fully controlled converter with RL load. Three-phase fully controlled converter with RL load. Just go through the circuit diagram here. Yes, this is a circuit representation of three-phase fully controlled converter or full wave converter with RL load. Here the circuit consisting same 6 SCRs which are numbered as T1 to T6 according to the sequence of firing of the SCRs. We will assign the numbers from T1 to T6 and combination of resistor and inductor is considered as the load. You know, depends upon the value of inductor. Here this converter is operates in two modes, either continuous conduction mode or discontinuous conduction mode. If you go through the high value of the inductor or large value of the inductor, then we are able to collect the continuous conduction mode. If you have the low value of the inductor, we are collecting the discontinuous conduction mode. First we go with the continuous conduction mode, later we discuss the discontinuous conduction mode of operation. So first go through the continuous conduction mode. You just draw the line voltages. You follow the procedure, simply take the reference line and below the reference line and above the reference line draw the two dotted lines. Later vertically you divide. This is 30 degrees for example, each one 30. You draw vertical lines. Like this. After that, for this first 4 boxes, you put the cross mark, this one, like this. And again next to 4 boxes, you put one cross mark. And next one, next one, next one, next one, and next one, next, like this. After that, you join the alternative peaks. From this, you ignore this one and next one, alternative peaks, like this. And similarly here also, and here also, and here also, and here also. The remaining one, this one, here it is, this one, this one, this one, and the bottom side also, here alternative peaks you add. Like this. So you take from this onwards as the reference. It is the reference. So you keep here 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360, 390, 420. And the first portion represents VCB, it is VAB, VAC, VBC, VBA, VCA, VCB. This one. So these are the line voltages. Now I just want to explain the operation of this 3-phase fully controlled converter with the RL load. Up to 60 degrees, this full wave converter, even it is under RL load, it behaves like R load. Up to alpha is equal to 60 degrees. So we are getting the same output voltage waveform. If you choose alpha is equal to 30 and alpha is equal to 60, you consider you are getting same output voltage waveforms like this. Even though we can consider the RL load, for alpha is equal to 30 and alpha is equal to 60, we are getting the same output voltage waveform. So now we will draw output voltage waveform for alpha is equal to 90 and 120. So here this is output voltage waveform for alpha is equal to 90 degrees. Now we go with alpha is equals to 90. Here we have the timing diagram, right? See. Now I just want to draw the output voltage waveform here. For alpha is equals to 90 degrees, I just want to draw the output voltage waveform. And second case, for alpha is equals to 120 degrees, we draw the output voltage waveform. V0. So for these two cases, first you draw the timing diagram. Later we will go with the output voltage waveform. So what is the timing diagram here? Just .30. So if you choose alpha is equals to 90 degrees, then where the T1 comes to the on state? Plus 60 degrees. So from 150 onwards, T1 comes to the on state from 150 to 270. Each SCR conducts for 120 degrees. After 270, T3 will come into the picture up to 390. After that, T5. So before T1, T5 will be in the on state. Ending portion is 150. Then what is the starting portion? 150 minus 120, 30. Between 30 to 150, T5 will be in the on state, before that T3. So that is the representation of positive group SER's conduction periods. If you go through the negative group SER's conduction period, if T1 is on at 150, where the T2 comes to on state? At 210. Why? Because the phase difference between positive group SER to the negative group SER is 60 degrees. So from this 210 to 330 T2, 330 to 450 T4. Before this T2 we have T6, ending portion is 120. Then what is the starting portion? This one. And similarly 0 to 90 T4. So from this timing diagram, here these are the conducting periods of negative group SERs. From this timing diagram, we will tabulate the voltage. So 0 to 30, which devices are in the on state? T3, T4. You first consider the positive group SER, later negative group SER. T3, T4. Then what is the output voltage? V0. Just 3, 4 na. So V0 is equals to VBA. From 30 to 90. 30 to 90. Which are in the on state? T5, T4. 5, 4. V0 is equals to VCA. 90 to 150. T5, T6. Then what is V0? VCB. 150 to 210. T1, T6. Then V0 is equals to 16 VAB. 210 to 270. T1, T2. Then V0 is equals to 12 VAC. 270 to 330. T3, T2. Then V0 is equals to 32 VBC. 330 to 390. T3, T4. V0 is equals to VBA. So where you start and end that portion, VBA. So these are the output voltage waveform. So from this voltage table, just you follow 0 to 30 VBA, 30 to 90 VCA, 90 to 150 VCB, like that. First we go with 0 to 30. What is the output voltage? VBA. Just go through that one. VBA 0 to 30. You first mention the periods: 30, 90, 150, 210, 270, 330, 390. So 0 to 30, what is the output voltage? VBA. So go through that VBA form. VBA line, this one. Here it is. VBA. This one. So you draw that portion like this. And next 30 to 90. What is that? VCA. See, 30 to 90. VCA. So where is the VCA line? VCA. This one. Here it is. Go through that. 30 to 90. This one. So like this. 30 to 60 positive half cycle, positive portion. 60 to 90 negative portion. And here it is VBA and it is VCA. After that VCB, VAB, VAC, like this. So here it is VCB, it is VAB, VAC, VBC, VBA. So this is the representation of output voltage waveform for alpha is equal to 90 degrees. What you observe here, if you go through the R load, there is no negative portions. Why? Because during this negative source voltage, the thyristors goes to the off state. But if you go through the VAB here, from 150 to 180, VAB means T1, T6 are in the on state. During that, there was some energy must be transmitted from source to the load. If T1, T2 are in the on state, what is the current flow through the circuit? From this phase A, T1, R, L, T6, phase B and the source. This is the current flow through the circuit when T1, T6 are in the on state. During that, there was some energy must be stored in the inductor. Even though the negative voltage is available across the source, due to the energy stored in the inductor, even though the negative voltage is available across the SCRs, due to the energy stored in the inductor, that energy stored in the inductor cause the extension of the conducting SCRs up to the next incoming SCRs. So, see here, from 150 to 180, you have the positive portion in the output voltage waveform. That means some energy is transmitted from source to the load. Due to that, there was some energy must be stored in the inductor. After that, this 180 to 210, next incoming SCRs are at 210. So, up to 210, the conduction of T1, T6 are extends. Hence why this negative portion of the source is available across the load. We already said in the output voltage waveform we have the positive portion, that is the representation of some energy is transmitted from source to the load. We have the negative portion in the output voltage waveform, that is the representation of some energy is transmitted from load to the source. So here from 150 to 180 some energy is transmitted from source to the load, and 180 to 210 some energy is transmitted from load to the source is there was some energy must be transmitted. So the resultant voltage across the load is 0. So how you are getting the 0 will be discussed. Okay. So here this is a representation of average DC output voltage. Voltage waveform representation for alpha is equal to 90 degrees. If you go through the R load, there is no negative pulses, only you have the positive portion. If you have inductor in the load, then depends upon the value of the inductor, you may get the negative pulses in the output voltage. If you have the high value of the inductor, then you are getting these continuous pulses. That means up to the next instant, see VAB up to 210, the negative portion is available from 180 to 210. Before 210, if the SCR goes to the off states, then that is discontinuous conduction mode. Later we will discuss. First we concentrate on continuous conduction mode. So for alpha is equals to 120, now I just want to draw the output voltage waveform. For that, first you draw the timing diagram for alpha is equals to 120 degrees. This is the last one. So what you are getting here, timing diagram, just draw the timing diagram. So if you choose alpha is equals to 120, then where the T1 comes to on state? At 180. So from 180 to 300. T1, 300 to 420. T3, next T5. Before T1, T5. Ending portion is 180, then what is the starting portion? 180 minus 120, 60, and between 0 to 60, T3. Here these are the conducting period of SCRs of positive group SCRs. If T1 is on at 180, where the T2 ons? Plus 60, from 240 to 360. After that T4. Before T2, T6, ending portion is 240, then what is the starting portion? 120, and between this 0 to 120 T4. So from this timing diagram, what is the output voltage? So from 0 to 60, T3, T4 are in the on state. If 3, 4 are in the on state, what is the output voltage? VBA. From 60 to 120, T5, T4. Then what is V0? 5, 4, VCA. 120 to 180, T5, T6, VCB. 180 to 240, T1, T6, V0 is equals to VAB. 240 to 300, T1, T2, V0 is equals to VAC. 300 to 360, T3, T2, then V0 is equals to VBC, and 360 to 420, T3, T4, V0 is equals to VBA. So where you start VBA and you end up to VBA. So from this you draw the output voltage waveform. From 0 to 60, what is the output voltage? VBA. Just you blindly follows the VBA line, 0 to 60. First you write the intervals, 60, 120, 180, 240, 300, 360. So 0 to 60 VBA na. So where is the VBA line? VBA, this one. You just follow the line. So here 0 to 60, this one. So 0 to 60. 60 to 120 VCA. Where is the VCA line? This one. You just follow the VCA here, 60 to 120, this portion. So this 120 to 180 VCB line, this one. So this is the VCB line. So 120 to 180, you just follow the VCB. Next VCA, VAB, VAC, VBC. So here it is VBA, it is VCA, it is VCB, VAB, AC, BC, and next VBA. Here the output voltage waveform simply represents the negative pulses, out and out negative pulses. Then what is that meaning? Here there was some energy is transmitted from load to the source. If you go through this output voltage waveforms, here as long as you maintain alpha lies between 0 to 90, you have only positive output voltage. Then the converter should operate as the rectifier. Some power is transmitted from source to the load. If you go through this alpha greater than 90 degrees like this, here for alpha greater than 90 degrees, the converter should operate as the inverter. The converter should operate as the inverter, which is called line commutated inverter. Which is called line commutated inverter. Line commutated inverter means even though the converter is energized by the AC supply, if the DC is converted into AC, that means the load will deliver some power to the source. That type of converter is called line commutated inverter. And here the average DC output voltage is simply given by V0 is equals to 3 VML by 5 cos alpha. Like continuous conduction mode, we already derived the average DC output voltage in continuous conduction mode. The same expression will be observed under RL load in continuous conduction mode. That is 3 VML by pi cos alpha. From this you conclude, if alpha is equals to 0, what is V naught? You are getting the maximum output voltage, which is 3 VML by pi. If you choose alpha equals to 90, then what is the V naught? 0. If alpha equals to 180, then V naught is equals to minus 3 VML by pi. So from this what you observe, if you go through the quadrant representation, if alpha lies between 0 to 90, then the converter is operates in the first quadrant, which is gives rectification operation, and the converter is operates as the rectifier. And if alpha greater than 90 degrees, then this converter is operates in the fourth quadrant, which gives the inversion operation. So what is that meaning of rectification? Means some energy is transmitted from source to the load, whereas if you maintain alpha greater than 90 degrees, then inversion operation should be taken place. Some energy is transmitted from load to the source. So if you want to collect two quadrant operation at a time, like first quadrant and the fourth quadrant operation, simply we go with the single phase fully controlled converter. Depends upon the firing angle. If alpha less than 90 degrees, you are getting the rectification. If alpha greater than 90 degrees, we are getting the inversion operation. This is the average DC output voltage and quadrant representation and output voltage waveforms for alpha is equals to, so for RL load in continuous conduction mode. If you go through the discontinuous conduction mode, we will see the output voltage waveform. Right. I just want to draw the output voltage waveform under discontinuous conduction mode. For same alpha is equal to 90 degrees. When you are in the discontinuous conduction mode for low value of the inductor. So timing diagram should be same from 0 to 90. For alpha is equal to 90, this is the timing diagram. From 0 to 30, VBA is the output voltage. You follow the VBA, 0 to 30. We mentioned this is 30, 90, 150, 210, 270 like that. So 0 to 30 VBA na, where is the VBA line? This one. So if we have this complete portion from 0 to 30, we are getting the continuous conduction mode. If we go through the discontinuous conduction mode, before 30, VBA goes to the off state. That means for 15 degrees take extinction angle, and here the output voltage is 0. 30 to 90 VCA. So 30 to 90 VCA, you follow VCA line, 30 to 60 positive and 60 to up to 75 only. Why? Because low value of the inductor, small amount of energy must be stored, and before the next incoming SCRs, the energy stores in the inductor is discharges. Then the present SCRs are goes to the off state. They don't maintain its on state up to the next incoming SCRs. What is the next incoming SCRs? At 90 degrees. Before 90 degrees, the SCRs goes to the off state, and so the negative output voltage becomes 0. So 30 to 60, we have the positive portion. After that 15 degrees and it is 0. Similarly 90 to 120, 120 to 135 negative pulse, 135 to 150 0. Similarly like this, like this. Here what we observe here, the output voltage 0, that means the energy stores in the inductor is completely discharges. So you have some current here and here charging current and discharging current. In this duration the current is 0. That is the representation of discontinuous conduction mode. Here it is the output voltage due to the VBA, it is VCA, it is VCB, and here it is VAB, VAC, VBC, VBA, like that. This is for discontinuous conduction mode. And if you go through the RLV loads, here this is the RL load under discontinuous conduction mode. And if you go with the RLE load in discontinuous conduction mode, if you go through the RLE load in continuous conduction mode, the same output voltage waveforms are observed like RL load under continuous conduction mode. Even though you go with the RLE load under continuous conduction mode, there is no difference between RL load and the RLE loads. If you go through the discontinuous conduction mode, then where the output voltage is 0, then back EMF is coming to the picture. Then what is the output voltage waveform? For same alpha is equal to 90 for RLE load under discontinuous conduction mode, the output voltage waveform becomes see here, the output voltage waveform becomes 0 to 15 negative spike and 15 to 30 0 na. So there you have the back EMF as the output voltage. After this positive, negative and again back EMF like this one. Very simple. Where the output voltage is 0, there the back EMF is coming to the picture. This is the representation of RL load in discontinuous conduction mode, and this is the output voltage waveform representation for alpha is equal to 120. Alpha is equals to 90 degrees with RLE load in discontinuous conduction mode. So this is a simple representation of 3-phase fully controlled converter with RL load. So where we use this full wave control converter means at a time if you want to collect the 2 quadrant operation like first quadrant operation, the fourth quadrant operations, then we go with the 3-phase full wave converters. If you want to collect single quadrant operation for the entire firing angle range, even our RL load or RLE loads, then we go with the semi converters or half controlled converters. So the next one is 3-phase semi converter or 3-phase half controlled converter. So next one, 3-phase semi converter or half control converter with R load. So what is the need of this semi converter means? For the entire firing angle range from 0 to 180 degrees, I just want to collect the only rectification, that is only first quadrant operation, I just want to collect, then we go with this 3-phase semi converter. So if you go through the circuit diagram of this 3-phase semi converter, with R load. Yes. So this is a simple representation of three-phase semi-converter or half-control converter. In the three-phase fully controlled converter, if you replace the negative group devices by the uncontrollable devices, then that is a simple representation of half-controlled converter or semi-converter. It consisting three ideal SCRs and three ideal diodes. So coming to this three-phase semi-converter or half-control converter with R load, it consisting three ideal SCRs which are numbered as T1, T2, T3 and three ideal diodes D1, D2, D3. So instead of here in full wave control converter you have T1, here you have T3, here you have T6 and here you have T2, here it is T4, here it is T6. So instead of these T4, T6, D2, we keep the diodes like D1, D2, D3. T1, T3, T6, T5, here you have T1, T2, T3. So this three-phase semi-converter or half-control converter is able to operate either as 6 pulse converter or 3 pulse converter, depends upon the firing angle. This converter is operates either 3 pulse converter or 6 pulse converter. First you go through the output voltage waveform, and one more thing, for this 3-phase semi converter we draw the output voltage waveforms for alpha is equal to 0, 30, 60, 90 degrees. First you draw the line voltages. Next, put the cross mark for 4 boxes each. And I'll join the alternative peaks. And ignore this first 30 degrees. After that you take the reference. This is the reference. Here it is G, this is 0. 30, 60, and this one is VCB, it is VAB, it is VAC, VBC, VBA, VCA, VCB. Right. So here I just want to draw the output voltage waveform. If you choose alpha is equal to 0 degrees, this is the output voltage waveform, no problem. I just want to take, okay, first we draw the timing diagram for alpha is equals to 0 degrees, then it is easy to understand. Here right. So if you choose alpha is equal to 0, where the T1 comes to the on state? 60 degrees, 60 to 180. T1. What is the next positive group SCR? T2. From 180 to 300. Next T4. 300 to 420. Next T. T3. Next T1. Before that T1, T3. Here these are the conduction period of positive group devices. Previously we have T1, T3, T5. Instead of T1, T3, T5 you have T1, T2, T3. Very, very important. T1, T2, T3. Again 1, 2, 3. That is the sequence. Right. If you choose alpha is equal to 0, T1 comes to the on state at 60. Okay. Negative group SCR conducts from 120 to 240. What is the negative group SCR actually? T2. Instead of T2, what here you have? Instead of T2, what you have here? D3. Here D3. See in the circuit, actually T2 is present here. Instead of T2, in semi-converter you have D3. Very, very important. So you mention that D3 here. Right. From 240 to 360. After T2, T4. Instead of T4, what you have here? D1. Next, D2. Before this D3, D1. These are the conducting period of negative group devices. From this 0 to 60, T3, D1, 3, 1 is nothing but VCA. This one is D2. Before D3, D2. Sorry. Before D3, D2. Yeah, 3, 2. VCB, VAB, output voltage will be same. This one, VCB, VAB, VAC, like that. Clear. Now, I just want to draw the timing diagram for alpha is equal to 30 degrees. For alpha equal to 30 degrees. Then what is the timing diagram here? Just you draw the timing diagram for alpha equal to 30. So if we choose alpha is equal to 30, where the T1 comes to on state? 90. 90 to 210. 210 to 330. 330 to 450. Before this T3. These are the representation of positive group SCRs. If you go through the negative group SCRs, the negative group devices consisting diodes. Those are uncontrollable devices. Even though you change the firing angle, the conducting periods of positive group SCR should be changed according to the firing angle, but the negative group devices conducting period cannot be changed. Why? Because those are uncontrollable devices. Hence why from 0 to 120, here continuously D2 will be on, 120 to 240, D3, 240 to 360, D1 and again D2. So from this what you observe? From 0 to 60, which are in the on state? T3, D2. Then what is the output voltage? 3,2. 3,2. V0 is equals to VCB. 60 to 90, which are in the on state? Sorry. 0 to 0 to 90, T3, D2. Okay. 90 to 120. 90 to 120, T1, D2. If T1, D2 are in the on state, 1, 2, VAB. V0 is equals to VAB. 120 to 210, T1, D3. 1, 3, V0 is equals to VAC. 210 to 240, T2, D3. 2, 3, V0 is equals to VBC. 240 to 330, T2, D1. Then V0 is equals to VBA. 2, 1. 330 to 360, T3, D1. V0 is equals to 3, 1, VCA. 360 to 450, again T3, D2, again V0 is equals to VCB. You are getting like this. So from this timing diagram, how the output voltage you draw? Go through this. 0 to 90, you put these intervals 0 to 90, 90 to 120, 120 to 210, 210 to 240, 240 to 330, 330 to 360, like this. So from 0 to 90, what is the output voltage? VCB. 0 to 90, you just follow the VCB, this one, VCB, like this. 90 to 120, what is the output voltage? VAB. So 90 to 120, you follow the VAB curve, this one, like this. And 120 to 210, VAC, like this. Next, VBC, VBA, VCA, like this. So here it is VCB, VAB, again VAC, VBC, VBA, VCA and VCB. This is the output voltage waveform for alpha is equal to 30 degrees. How many pulses are generating here? 1, 2, 3, 4, 5, 6. 6 pulses are generated. Okay, good. Now I just want to draw the output voltage waveform for alpha is equals to 60 degrees. For alpha equal to 60 degrees. Then what is the timing diagram here? Thirty, 60, like this. If you choose alpha is equal to 60, where the T1 comes to on state, plus 60, like 120 to 240, T1, 240 to 360, T2, T3, 0 to T1 also T3. Negative group unchanged. What you are getting here? D2, D2, D3, D1, D2. So what is the output voltage table? 0 to 120, T3, D2, 120 to 240, T1, D3. 240 to 360, T2, D1. Next, 360 to 480, again T3, D2. So if T3, D2 is on, 3, 2, what is the V0 here? VCB. 120 to 240, 13, VAC. 240 to 360, 21, VBA. Then output voltage becomes 0 to 120, VCB. Where the VCB line? C. Here output voltage for alpha is equal to 60, VCB na, this one, like this, 120 to 240, VAC. Where is VAC? This one. VBA. Like this. So it is VCB, VAC, VBA. So this is the output voltage waveform for three-phase semi-converter for alpha equal to 60 degrees. What you observe here? For alpha less than or equal to 60, here we are able to collect the 6 pulses. For alpha is equal to 60 or greater than 60, we are able to collect the 3 pulse converter. See here how many pulses are generated here for completion of one full cycle up to 360, only 3 pulses. So it should be operates as 3 pulse converter. This is the representation of 3-phase semi converter for alpha equal to 30 and alpha is equal to 60. And if you go with output voltage waveform for alpha is equals to 90, what you observe here? For alpha equal to 90, just draw the timing diagram. For alpha is equals to 90, if alpha is equal to 90, where the T1 comes to the on state at 150, 150 to 270, T1, 270 to 390, T2, next to T3, ending portion is 150 and starting portion is 30. Negative groups are unchanged, 0 to 120 is D2, 120 to 240 is D3, D1, D2. So from this 0 to 30, what are the conducting devices? T2, D2. Then output voltage is 0. Why? Because T2, D2 must lies on the same leg. Voltage across the short circuit is 0. Then output voltage 0. And 30 to 120. T3, D2. 3 to on in the on state, then V0 is equals to VCB. Similarly, 120 to 150, T3 D3 must lies on the same leg, again output voltage 0. 150 to 240, T1 D3, then 13, output voltage is VAC. Similarly, 240 to 270, T1 D1, then output voltage is 0. 270 to 360, T1 T2 D1, then output voltage VBC. You just follow this table. 0 to 30, output voltage is 0. Mention here 30, 120, 150, 240, 270, 360. Then 0 to 30 output voltage is 0, and again here VCB, again 0 VAC, again 0 VBA, again this one is VCB, VAB, VAC. Like this. So discontinuous conduction mode, alpha less than 60, three-phase semi-converter is operates in continuous conduction mode and it acts as the 6-pulse converter. If alpha greater than or equal to 60 degrees, it is operates in discontinuous conduction mode and we are getting 3 pulses, 1, 2, 3 for completion of one full cycle. This is a simple representation of three-phase semi-converter with R load. And if you go with the average DC output voltage, again here we have the two cases. Right. First one, case 1, alpha less than 60 degrees in continuous conduction mode. The average DC output voltage is V0 is equals to, how many pulses you have generated? 3 pulses, like total 6 pulses, but 3 pulses have one duration and 3 pulses have another duration. If you choose alpha is equal to 0, then VCB 60 degrees and VAB 60 degrees. Okay. If you choose alpha equal to 30, VCB is 90 degrees, VAB is 30 degrees. If you choose alpha equal to 60, VCB is 120 degrees and VAB is 0. That means if alpha less than 60 degrees, 3 pulses should have same time period and 3 pulses should have another time period. Hence, so you take common those 3 and for the remaining these 2 pulses you write the timing interval. So what is the time interval here? If you go through the VCB, if alpha is 0 to 60 degrees, alpha equal to 30, 90 degrees, then the duration should be written like V0 is equals to 3 by 2 pi, limitations are 60 plus alpha to 120 VML sin omega t d omega t plus integral 60 to 120 plus alpha VML sin omega t d omega t. These are the limitations. If you choose alpha equal to 60 to 120, 60 to 120, no problem. If you choose alpha equal to 30, 90 to 120, 60 to 180, 120 degrees. If you choose alpha equal to 60, 120 to 120, this is 0 and 60 to 180, 120 degrees duration. So we will fulfill the limitations like this: 60 plus alpha to 120 VML sin omega t d omega t plus 60 to 120 plus alpha VML sin omega t d omega t. By simplify this expression, what you will getting here? 3 by 2 pi take VML outside. So 3 VML by 2 pi. Integral sin omega t is minus cos omega t between the limits 60 plus alpha to 120 plus minus cos omega t between the limits 60 to 120 plus alpha. So what you are getting here, 3 VML by 2 pi minus cos 120 plus cos 60 plus alpha minus cos 120 plus alpha minus cos 60. Three VML by 2 pi integral. So minus cos 120 means sin 90 plus 30, cos 90 plus 30 minus sin 30, minus sin 30 is minus 1 by 2. So minus of minus plus 1 by 2 and cos 60 is 1 by 2, these two gets cancelled, and this 2 is written as, finally by simplifying this, 2 cos 60 cos alpha. So what you are getting here, cos 60 is 1 by 2. So finally V naught is equals to 3 VML by 2 pi cos alpha. This is the average DC output voltage under continuous conduction mode. And if you go through the case 2, alpha greater than 60 degrees, then the average DC output voltage is V naught is equals to, we are able to generate the 3 pulses, hence by 3 VML by 2 pi integral limitations are alpha to pi VML sin omega t d omega t. So by simplifying this, 3 VML by 2 pi into 1 plus cos alpha. Here this is the average DC output voltage under discontinuous conduction mode with R load for alpha greater than 60 degrees. So in this class we just discussed the 3-phase fully controlled converter with RL load and different firing angles, and 3-phase semi converter with R load for different firing angles alpha 0, 30, 60, 90 degrees. And in the next class we are going to discuss about the effect of source inductance. Up to that we are going to end the second unit. Thank you.